Hello everyone, welcome to my presentation, Differential Testing of Decoders with the Instruction Operand Inferring Algorithm. My name is Guang Wang. I am a PhD student from Institute of Information Engineering, Chinese Academy of Sciences. This is the talk outline of my presentation. The decoders decompose the binary code into an instruction semantics operation. For example, the first binary code is decoded into an add instruction. The second binary code cannot be decoded. The decoder returns an invalid assemble code semantics. Decoders are tools for software analysis, sandboxing, malware detection, and undocumented instruction detection. However, the decoders may produce different semantics or results when decode the binary instruction. It is necessary to test the decoders to find the difference and fix the errors, bugs, and vulnerabilities. An x86 instruction must have an opcode. The other fields are optional. The instruction space is divided into legal instruction space and the reserved instruction space. The instructions defined by the CPU manufacturers are located in the legal instruction space. The undocumented instructions and the invalid instructions are located in the reserved instruction space. Decoders for x86 need to decode variable length instructions up to 15 bytes long, which results in 2 to the power 120 possible instruction cases. The motivation of our method. The problem is that the state-of-the-art methods to test the decoders cannot systematically cover the reserved instruction space. However, the reserved instruction space is important in the detection of undocumented instructions. Our goal is to test the reserved instruction space and the legal instruction space systematically. We analyze the depth-first search method in the SandSifter. SandSifter is specifically for undocumented instruction detection on x86 processors. It tests the legal instruction space and the reserved instruction space. However, it still tests considerable immediate and displacement operand. We proposed an instruction operand inferring algorithm. Our method reduces the test of the immediate and the displacement values, and our method does not influence the testing of the reserved instruction space. To describe the x86 instruction space in detail, we separate the 15-byte instruction space into 5 parts. There are 3 kinds of opcode format, as shown in the figure. Our goal is to test all the elements in V2, V3, and V4, and to test the minimal subset of V5. Thus, our method only tests the valuable instruction space. The overall framework. Our main contribution is the instruction generation module and the comparison module. The instruction generation module generates instructions. We name our instruction generation method DFSGen. The comparison module sets the rules for comparison of decoders and the processor. We represent a legal instruction as a tree, where the root is the opcode byte or the prefix byte. The nodes on the path from the root to the leaves represent the various bytes that compose the instruction. The instruction space we test starts from a 15-byte string. SandSifter uses the instruction length to get the generation of the instructions. SandSifter tests 256 immediate and displacement values in the instructions that have immediate and displacement operand. Our algorithm avoids the generation of redundant test cases by identifying the feature values. Once the algorithm recognizes the feature values, the index value is reduced by 1. Our algorithm ends the traversal of the displacement operand early. Then the next new type of instruction is generated. How to get the feature values? Ideally, any values from 0 to FF can be used as the trigger to end the traversal of the immediate or displacement field early. The algorithm needs at least one new instruction to get the new instruction length, so 0 cannot be the feature value. For the displacement operand, the feature value is 1. For the immediate operand, the feature value is 2. How to use the feature values? The code on the left side is the overall framework of our algorithm. If it is a legal instruction, our algorithm skips the redundant operand. If it is a reserved instruction, our algorithm traverses the instruction space. The instruction Operand Inferring algorithm is implemented in the skip operand function. The details of the algorithm is shown on the right side of the slide. As a result, our algorithm only tests 2 displacement values in the add instruction. Our algorithm only tests 3 immediate values when the legal instruction has immediate operand. Thus, the test efficiency is improved. The idea of differential testing is to compare the test results produced by different decoders. We judge the output of the decoders in 2 steps. First, the algorithm determines the instruction is over-accept or under-accept to the decoders. Then the algorithm determines whether the instruction mis-accept based on the instruction information. For example, the instruction length. We evaluated the effectiveness of our method on both the Intel and AMD processors, and the evaluation environment is listed on the slide. As shown in the table, there are more than 4 million inconsistent instructions between Capstone and XCCD. These slides show the instructions that cannot be decoded by Capstone but can be decoded by XCCD. These instructions should be valid, but Capstone cannot decode them. We compare the DFS gen and sense shifter. By contrast, the overall efficiency of our method has increased by about 4 times, and our algorithm does not shrink the reserved instruction space. We compare DFS gen's method with the state-of-the-art methods of instruction test case generation. In summary, our method has a better coverage of the instruction types and higher efficiency. In conclusion, DFS gens covers both legal instruction space and the reserved instruction space. We implement our method on Capstone and XCCD and find the difference between them. The efficiency of DFS gen is about 4 times than the method in sense shifter. Our future work is to implement the method on more decoders and to research the method to skip the redundant prefix combinations when the number of instruction prefix is greater than 1. Thanks for listening. Any questions?